All right, so what I wanted to do for the last class was give a little bit of a sense of where all of this goes and connect the various things we've been doing. Now, of course, in one lecture it's going to be impossible to do a complete connection, but I want to give you a sense of how some of the different units fall together, what kind of techniques do you need to use, what kind of problems are people studying. If there's time today, I'm actually going to try to do a problem that's related to some current research that I'm doing with Blake and some other students from last summer, and we'll just try to see if we can actually solve it live in the class. All right, so what I want to do is I want to talk about low-lying zeros. The fact that it has GL2 L functions in the title makes it quite clear that this was not designed for today's lecture. The fact that it also says October 22nd, 2012 is another good giveaway. GL2, for our purposes, just means when you look at the Euler product, there are two factors. So the Riemann zeta function, we can write it as a product over primes of 1 minus 1 over p to the s inverse. There's just one factor for each prime. If you have two factors, 1 minus alpha p over p to the s, 1 minus beta p to the minus s, that's called an Euler product of degree 2. Degree 3 and higher follows naturally. There's lots of connections as to where these come from. And we're not going to talk about that at all. This leads into the Langlands program. If I give you a series, the sum of an over n to the s, as long as the an's don't grow too fast, the series will converge. But most of the time it'll be useless for anything you care about. So the question is, when can you choose good values of an to get something that has some hope of helping you understand something in arithmetic, something in number theory, something in combinatorics? So we've already seen some examples. Fortunately, one of the most important examples is one of the easiest examples. So if you had your choice for the an's, other than the trivial choice of all zeros, which I will not let you get away with, what would be your next simplest choice? All ones. Fortunately, that's the Riemann zeta function. Okay, so even at that point, it's already interesting. The next choice is to use Dirichlet characters. So now the an will be chi of n, where chi is a character modulo some number m. And we saw these when we looked at primes in arithmetic progression. If you want to start getting up onto GL2, you can start looking at elliptic curves. So if I give you y squared is x cubed plus ax plus b, and I want to count how many solutions are there. Well, I can ask how many solutions are there over the complex numbers, in which case it's damn easy. Take an x, take a square root of x cubed plus ax plus b. Looking for real solutions is harder. Looking for rational solutions is even harder. Looking for integer solutions. But you can also then make things a little bit easier and say, what if I look at solutions modulo p? And say y squared is congruent to x cubed plus ax plus b. And if I do that, it turns out it's much easier to count how many solutions there are modulo p within a certain accuracy, and I can then use those as my coefficients AP and build up a L function that way. So we're going to, for the most part, ignore too much about where the stuff is coming from, but this is a huge area of research right now. All right, introduction. So here's a couple of problems of why we might want to study L functions. So some of these we've covered in class, the infinitude of primes, primes in arithmetic progression, and this is just the Riemann zeta function and Dirichlet L functions. The next is Chebyshev's bias, which we've talked about a little bit. Pi 3 4 of x, this is the number of primes congruent to 3 mod 4. Most of the time is greater than or equal to the number of primes congruent to 1 mod 4. In fact, I was just talking at the conference at Banff with Mike Rubinstein, who was one of the key people in advancing our understanding of this. This is one of the best honest theses in the history, I think, of mathematics. He was an undergraduate at Princeton at the time, and off the record I will tell you some stories about the computations and the amount of resources taken at Princeton for that. Next is the Birch-Swinnerton-Dyack conjecture. This is one of the Clay Millennial Prizes. If you are looking for hard ways to earn $1 million, this is definitely one of your 6 best choices in that regard. And what it says is, going back to the elliptic curves I mentioned a while ago, you can look at the group of rational solutions. And you can ask, all right, it turns out that this is an abelian group. It's finitely generated. What are the numbers of generators of the infinite component? So it turns out you have a lattice, some number of copies of z. How many copies of z do you have? That's called the geometric rank. It's conjectured that if you look at the L function attached to an elliptic curve, the order of vanishing of the L function at the central point at s equals 1/2 is equal to the order of the geometric group. So if you want to count them, you can do it either way. And this is a wonderful interplay between local information and global information. That's how you should look at all of this. Is locally I can count how many solutions are there modulo p, piece that all together, and then I get some information about the global thing, counting rational solutions. We've seen a lot of this local global stuff before. If you think back to what we did on the circle method, we skipped a lot of the details. I left that for you to read in the book, but we had these products over primes or products over q's, and we had the singular series. And we took local information and we put that together to finish up the main term. And we saw that if we ever had a local obstruction that prevented us from getting solutions, as long as there were no local obstructions, we got some solutions. Other problems, gets a little bit more involved. Uses algebraic number theory, counting the class number. Has anybody here taken algebraic number theory? So I'll skip the class number, but it turns out it's related to stuff like that. So here is how distribution of zeros can help us. So in terms of proving the prime number theorem, what we saw, which was really nice, is we just needed the Riemann zeta function was non-zero on the line real part of s equals 1 to prove the prime number theorem. We got an error term that's not worth writing home about, but we were able to prove the prime number theorem. The main term is larger than the error term. Similarly, for primes and arithmetic progressions, we just need to know what's going on at the edge of the critical strip. Now, if we want a better count of how many primes there are, we think that the error term is not nearly as large as we get when we just use the information about what's going on at the real part of s equals 1. If we assume the generalized Riemann hypothesis, then we get the errors about square root of x if you want to count primes up to x, or maybe x to the 1/2 log x, something like that. If you think about where else G or H came in, when we go back to the circle method, and I wasn't talking about the circle method at Michigan, but when you go back to the circle method, that was one of the key inputs Hardy and Littlewood did. And they said, hey, if we assume this stuff about the Riemann hypothesis, we can now have some understanding of these generating functions. And when we understand these generating functions, we can use it to solve problems. The next thing was Chebyshev's bias. So this is one of my favorite assumptions. It's called GSH, the grand simplicity hypothesis. And what it says is the following. I need a notion from linear algebra. I need the notion of independence. So we say a set of vectors is independent if the linear combination equals 0 implies the coefficients equal 0. Not surprisingly, linear independence is a function of what your base field is. So 1 and pi are independent over the rationals, but they're not independent over the complex numbers or over the reals. As a nice exercise, and it's not a hard one, try to figure out a linear combination of 1 and pi that's 0 over the real numbers. Right? That's not too bad. But trying to do it over the rationals, can't do it. The grand simplicity hypothesis says, look at all the zeros of Dirichlet L functions, except for the zeros at the central point, they're all linearly independent over the rationals. Because really, how could they not? And so it turns out there's something called the function field. And in the function field setting, GSH can actually fail, and GOH is actually a theorem. The function field is very different than the number field in terms of what we're able to show. So there are situations where GSH is false, but we believe these zeros are so complicated and that they're behaving independently that their combinations should be linearly independent. The question is, how the hell does that help us? The reason it helps us is when you're looking at these calculations for primes and arithmetic progressions and trying to see which one is more than another, it turns out you're flowing on an n-dimensional torus, where n is the number of zeros you're looking at simultaneously. And you want to make sure that you flow uniformly and you hit all possible spaces. So in class, we proved that if alpha is irrational, then n alpha mod 1 is equidistributed. We never did this in class, but there's generalizations in the book. What if I give you a couple of numbers that are linearly independent over the rationals? What if I give you alpha and beta are linearly independent, and then look at n alpha plus m beta, or maybe n alpha plus n beta? Does that uniformly flow in the square? And we need something like that in general when we're trying to look at primes in arithmetic progressions to see a bias. We want to see that something is flowing uniformly. And that's where GSH is coming from, to say, hey, these different zeros, their real parts are, or their imaginary parts are all linearly independent. You'll flow uniformly over the whole thing. And I'm skipping the class number consistently. So we just saw that the more information we know about the zeros, the harder problems we can solve. We went from being able to talk about there's infinitely many primes to what's our error term to biases between the different classes. So what are our goals for today? I want to determine the right scale to study problems. This is very similar to what we were doing in random matrix here. If we have an n by n matrix, what's the correct scale to look at for the eigenvalues? And not surprisingly, depending on the size of the matrix, we need to normalize the eigenvalues by something else. So we saw that 2 square roots of n worked really well for real symmetric matrices. The 2 is just so we can use the fancy word semicircle rather than semi-ellipse. It's the square root of n that really matters. Well, when we look at zeros of L functions, what's the correct way to normalize the zeros of L functions so that we can compare different L functions? It turns out the behavior is a little bit different near the central point than high up on the critical line. So we're going to see similar behavior in number theory and random matrix theory. I'll discuss some of the tools and techniques. I'm probably not going to talk at all about new results in GL2, since we don't really do too much on GL2 in this family. Instead, I'm going to concentrate on some of the ideas for Dirichlet L functions. Okay, so here, in a nutshell, this basically describes my life. I spend my life, studying spacings between events, waiting until something interesting happens. Anybody watch The Incredibles? Yeah, just the little kid who's waiting outside. You're waiting for something to happen, and then just happens to be in the right place at the right time. So what can I study? I can study the spacings between energy levels of heavy nuclei, eigenvalues of matrices, primes, the fractional parts of n to the k alpha mod 1, zeros of L functions. The same ideas apply to a lot of these problems. The actual computations can be different, but the whole formulation is how long do you have to wait before something interesting happens? There's other ways you can study waiting. Anybody know what company is really good at studying waiting? Life insurance. Waiting until people die. Different type of waiting. On a more positive note, the Disney company. Managing people's line waits. Very, very good at studying waiting. Another example is you're all probably far too young to remember when banks used to have 4 tellers and 4 lines. And now they have 1 line that feeds into the 4 tellers. And the reason is this way: if you get that special person with all those extra requests, they don't knock out and have a horrible line experience for everybody behind them. They just knock out 1 teller from circulation. The average wait time doesn't change. But the variance in wait time, you have a couple people who got a really bad experience. This is why banks have moved to 1 line, 4 tellers. If you look at going through security at airports, why don't we do this at supermarkets? I'm sorry? Some supermarkets do this, but most supermarkets do not have 1 massive line feeding into all the different cashiers.
Shopping carts?
Yeah, shopping carts. Yeah, we've got to figure out how to make the shopping carts smaller and have people, well, no, that's not the supermarket's goal. They want you buying stuff. They want you filling up the shopping cart. So for the supermarket, it does not make sense to try to reduce to 1 line feeding into all the cashiers. But they still have thought about different ways. They now have portable scanners that a lot of people use. They have self-checkout lines. So the idea of trying to study waiting between events, if you don't care about things like zeros of L functions, there are other situations where a lot of these techniques are applicable. In probability theory, they talk about these models all the time. Okay, so in studying the statistics, there are 3 key steps. Step 1 is determine the correct scale to study. This is basically the ante you need to come into the game. What's the right scale so that things are comparable? The next is we want some kind of explicit formula relating what we want to study to something we know. So in random matrix theory, what did we have that played this role? The eigenvalue trace lemma. If I ever get to teach linear algebra at Williams, this will be one of the huge highlights of the course, is getting to the eigenvalue trace lemma. We need analogs of this in number theory. And it turns out there are analogs, and they allow you to convert from sums over zeros to sums over primes. And it's typically proved using complex analysis, but it does play the role of the eigenvalue trace lemma. The eigenvalue trace lemma, however, would be absolutely useless if we didn't have a way to then execute the sums. And in random matrix theory, well, what did we see? We saw we had integrals of products of matrix coefficients times nice density functions. And we just got moments and tuples of moments. And those integrals were easy to do. In number theory, it turns out that what comes out is much, much harder, and we don't have good ways to handle this. We don't have as good averaging formulas in number theory as we do in random matrix theory. We've seen a couple of examples. We've seen, for instance, things like Dirichlet's orthogonality relations for the characters. And we can use that to execute sums over the family. And those will be extremely useful in trying to understand what's going on. The last thing is, and it's in red because I really want to emphasize this point, it is not always trivial to figure out what is the correct statistic to study. If I wasn't sick, I would be more emphatic right now, but I am recovering from travel. I was talking with some colleagues years ago. This was my thesis advisor, one of my thesis advisors, Peter Sarnak, and his colleague Zev Rubnik. And one of them said it took them 6 months, one of them said it took them 9 months to figure out what was the correct statistic to study in their Duke paper on correlations of zeros of L functions. And if you've ever done any combinatorics or any of these expressions, if you look at things the right way, it's often much, much easier and everything simplifies. But when you have these very painful expressions, it's not always clear how to proceed. And so we've seen this time and time again in terms of analyzing these functions. One nice example was in the circle method. We saw that if we evaluated it at a rational with a small denominator, then all that really mattered is, we have a sum over primes. What is that prime congruent to modulo q? And then we split it up into different residue classes, and then each one we kind of apply things, and then try to piece it all together. So unfortunately, it often takes a while to figure out what the right statistic is. Fortunately, once somebody figures that out, you can then try applying the statistic to other problems. And so a lot of my work is just brick building, is now that we have these statistics to look at, I've looked at them in various situations. It's often non-trivial to do the calculations, but it's even harder to figure out what's the right thing to look at. For a long time, in fact, people missed differences in L functions because they were not looking at the right statistic. They were looking at only what was going on very far away from the central point. And I'll talk a little bit more about that in a moment. Okay, so quickly reviewing classical random matrix theory. So this should not be too bad for us because we've just done random matrix theory, so we're going to go through this a little bit fast. So classical mechanics, the three-body problem is intractable. So if I give you 3 points under gravity, can't do it. 1 point, no problem. 2 points, no problem. 3 points in general configuration, we can't. So imagine something like uranium with over 200 protons and neutrons and a far worse force of interaction. So the fundamental thing in, no, is this working? No, okay. The fundamental equation in quantum mechanics is you have some matrix H, it acts on the energy eigenstates, and En is the energy eigenlevels. So as I remarked in class, this is an infinite by infinite matrix and we don't know any of the entries. So good luck diagonalizing this, good luck calculating the eigenvalues. But that's what we're trying to do. So the idea that Vigna had was to use the complications of the system to help us, to say that most things average out. And so we talked about molecules moving back and forth. And so with molecules moving back and forth, you want to calculate how many things hit a wall in a given amount of time. Well, you look and see how many things are close. And then for each configuration, you calculate what's the probability you have that configuration. You calculate the pressure for that configuration. You average over all configurations suitably weighted. And this gives you the average pressure. And then you just cross your fingers, click your heels 3 times, whatever, and just pray that the system average is close to what you're actually observing. And this is some kind of central limit theorem. And for the most part, this actually works. And this is one of the reasons why we have such great universality and why you see such varied systems exhibiting similar behavior. And then, of course, depending on what kind of system you have, you might have some constraints over your matrix A. Okay. So what comes next? Well, this is the classical random matrix ensembles. So first we'll have a real symmetric matrix. So Aij is Aji. We choose the matrix elements that are independent, randomly and independently from some fixed distribution. Nowadays, we don't do this anymore. In number theory, we choose things from subsets of unitary matrices with Haar measure. That way, there's a more natural notion of randomness. It turns out if I give you a classical compact group, you can put on a measure on the system. For us, we'll just use the classical thing we've done in class. And we can talk about what's the probability my matrix is chosen. Well, what I really mean is the probability that I choose a matrix in a little window or a little box around that matrix. And so I just integrate my probability density function from, say, alpha ij to beta ij, and I take the product. Not surprisingly, if alpha ij is minus infinity and beta ij is positive infinity, all the integrals are 1, and I've covered the whole space. And then you can see how likely am I to be, say, all of my entries within epsilon of the identity. And you'll see that's extremely small. Okay, so delta is the Dirac delta function. It's essentially putting a unit point mass at the point x naught. And so if I integrate a function f against the delta function at x minus x naught, I just get back the value of the function at x naught. So we saw this, I think, when we were doing approximations to the identity and we were doing Fayet's theorem. And this was one of the key proofs, or the key ingredients in the proof that the Fayet series converges for nice functions. And now, so to each a, we attach a probability measure. We put a massive size 1 over n at each of the normalized eigenvalues. And again, the 2 is not important. It's the square root of n that really matters. So if we want to now calculate how many normalized eigenvalues do we have in the interval ab, well, we just integrate from a to b. And we can calculate the kth moment. And now we have the sum of lambda I of a to the k. And this is where we use the eigenvalue trace lemma. It's just the trace of a to the k. All right, so this is not the most general way to phrase it, but this is more than good enough for our purposes. This is Vigna Semicircle Law. If you have n by n real symmetric matrices, independent, identically distributed entries coming from a fixed distribution, mean 0, variance 1, other moments finite, then for almost all a as n tends to infinity, the probability of normalized eigenvalues is just given by integrating the semicircle measure from a to b. So I actually got to see Vigna's Nobel Prize. It was on display in the library at the math physics departments at Princeton. And this is one of the key things he is famous for. My thesis advisor and my main mentor when I was undergraduate at Yale, Frank Firk, was one of the original people gathering the nuclear data on energy levels of heavy nuclei that led people to formulate these conjectures. And so it's very easy to forget how important it is to gather data. If you're a theorist, you sometimes look down on the experimentalists. This is not a good mentality to have. It is a lot of times these numerical explorations become crucial in terms of trying to figure out what's going on. They give you the clues and the signals. They tell you what's interesting. And if there's time today, I'm not sure there is, I will talk about some of the work the bias group and I were doing this past summer on moments of elliptic curve coefficients. But these numerical data, these explorations are extremely important. They're often very difficult. In nuclear physics, they have on the order of 1,000 data points. And with 1,000 data points, sometimes it's very hard to see the behavior that's going on. And you have to go a little bit out on a limb in terms of conjecturing what you think is happening at that time. In Riemann's time, the computational resources were not nearly as good as they are now. I think did I read to you, the Riemann hypothesis in his paper, this casual aside? If not, if you ever think that I make side remarks, you should see how the Riemann hypothesis is presented. It's as it's not really relevant to the problem at hand. After some brief attempts at proving it, we move on. And so it's a really, really nice just throwaway. Now, what Riemann doesn't say, and I don't know exactly when he did this, he actually calculated the first couple of zeros of the Riemann zeta function on the critical line. And he had developed a formula to do this, and the formula was then lost. He never mentioned it. And when Siegel was looking through Riemann's archives in the University of Göttingen, maybe 70 years later, he discovered it among Riemann's papers. He found these papers with scribbles. Wait a minute, this looks like the second zero. And so he actually had the first 6 zeros calculated and just didn't tell people. And he had seen that they were all on the line. And he had a better formula than people had been using in the intervening 70 years. This also gives a good emphasis to the statement, read the masters. Go back and look at what they've been doing. One of the four Fields medalists this year, Manjul Bhargava, when he was a grad student at Princeton, he went back and he read Gauss. And he looked at some of the things Gauss had looked at that people had really stopped and hadn't had much success with in 200 years, and he found great ways to attack them. All right, so here's the sketch of the proof. So we've talked about the eigenvalue trace lemma and why it's important. It relates the sum of the matrix elements, which we understand, those are what we choose, to the eigenvalues, which is what we want. And so we talked about how to get the correct scale. So the trace of a squared is just the sum of the eigenvalues of a squared. So the central limit theorem basically tells us that it should be of size n squared with fluctuations roughly of size. How big do you think the fluctuation should be? Roughly of size n. Right? We have n squared elements. Each aij squared is on average 1. The variance of a sum is the sum of the variances. So the variance should be of size n squared. The standard deviation is the square root. It should be of size n. So we expect this sum to be of size n squared. And we expect it to be pretty tight about that. And so now, given that the sum of the squares is about size n squared, then we expect on average each one of them is about square root of n. Is this a proof? I mean, we've passed a square root through the average, but this does give us a strong evidence, strong suggestion of how we should normalize things. All right, so now the kth moment is just the trace of a to the k over some powers of 2 and n, and so now we're left with this integral that we need to do. And again, what's nice is it's a polynomial integral, and it's all going to come down to combinatorics. So the second moment is so easy, it hides what's going on. So for the second moment, we have the sum over I, sum over j, aij squared. I don't know why I wrote it as aji squared. At least I fixed it on the next line. And then all the integrals become 1 except for the integral involving aij squared. Because everything is nice, we can interchange the integrals in the sum. And so we get we get 1 coming from this, and then we get lots of 1s coming from that. The fourth moment and the high moments become far more involved, and depending on what kind of system you're looking at, you have very different combinatorics. So we saw quickly that things have to be matched in pairs. Well, if anything was not matched in a pair, if it was standing by itself, since its expected value is 0, the contribution would be 0. And so there's lots of different ensembles we can look at. So here's looking at 500 matrices. I'm choosing the entries from a Gaussian. They're 400 by 400. And it looks pretty good in terms of looking like a Gaussian. This is the Cauchy distribution, one of my favorites. So hopefully you can see a slight difference between the density of eigenvalues between the Cauchy and the Gaussian. Does this violate Vigna Semicircle Law? Nope. Why not? Yeah, Cauchy has infinite moments. We can argue, if you want, for the next 25 minutes, I don't think it's the most effective use of class, as to whether or not the Cauchy distribution has mean 0. It's not arguable, or at least not well arguable, that the Cauchy distribution has finite variance. It has infinite variance. And so it does not satisfy the conditions of Vigna semicircle. So the GUE conjecture is that if you choose any nice probability p, the spacings between adjacent normalized eigenvalues converges to something universal, which looks a lot like x e to the minus constant x squared. This has now been proved. When I was an undergraduate, this was open. This is very, very recent work in the last 5 years or so. So looking at spacings between adjacent eigenvalues, adjacent normalized eigenvalues. So I'm choosing 5,300 by 300 uniform matrices. And so the black line is the prediction, the blue is the histogram. It's actually a little bit of a lie. The black line is not the prediction. The black line is the close approximation to the prediction. I don't want to calculate the infinite Fredholm determinant. The approximation is really close, just using the approximation. Good fit, bad fit. Good fit. Cauchy distribution, good fit, bad fit. All right. So here's the uniform again, here's the Cauchy. Is it a fair comparison to say the Cauchy is worse? So here's the uniform, here's the Cauchy. Is it fair to say the Cauchy is worse? Why? Yeah, I'm only looking at 100 by 100 Cauchys. Here I'm looking at 300 by 300 uniforms. What should we do? Yes. So either make the uniforms smaller, which does not seem like a good idea, or take larger Cauchy matrices. 300 by 300 Cauchy. So this is to me, one of the most fascinating parts of random matrix theory, is this remarkable universality. This density of states, how many things you have happening, that varies greatly from system to system. But the spacing between things that happen is universal. Think of this almost like the central limit theorem. So many different systems in number theory follow central limit theorem. It's the same thing here with spacings between events. There are not that many different spacings between events. There's GOE spacing, there's exponential spacing. There's not that many possibilities. And so even though the density of states is different, the spacings between events is, we believe, the same. Here's another example. This is the adjacency matrix of a graph. So a graph is a collection of vertices and edges. We put in the entry aij the number of edges connecting vertex I and vertex j. Typically, you would look at simple graphs where you don't have multiple edges. So as an example of why you might want to look at something like this, imagine, I don't know, you're in charge of the US military forces. It may be extremely important at times for you to communicate with certain generals or units in the field. You might want to have more than one way of reaching them. Right? And so there could be some situations where you might want to have redundant measures. I would hope the US and Russia have multiple hotlines, so that if something is down with the first one, we cannot complete your call as Dal, you had the ability to quickly move to something else. In general, though, you often, when you're building systems, you might just have at most one connection between various things. Well, this gives me a real symmetric matrix. We often look at d-regular graphs. A graph is d-regular if each vertex has d edges coming out of it. So this would not be a d-regular graph. D-regular graphs have a lot of very nice properties. And we can ask, what can you say about the eigenvalues of such matrices? And so the density of eigenvalues for d-regular graphs is given by Keston's measure, and this is d equals 3. Semicircle or not semicircle? Yeah, but then you get the stuff going on at the edges, so semicircle or not semicircle. But now let's look at what happens as d goes to infinity. So if you look over here, we have x is less than or equal to 2 square roots of d. So x is about 2 root d. When d gets very, very large, d squared minus x squared is of size 4d. D squared minus x squared is essentially d squared. This factor over here on the outside becomes insignificant in the limit as d goes to infinity. So as the degree of regularity becomes larger, what that means is more and more vertices are talking to each other. And you're going to still let the size of your graph go to infinity. It looks like the graph is going to become freer. If you think about what a two regular graph looks like. So for a two regular graph, each vertex is connected to two others. Well, if I start here, I have two neighbors. Each of those have two neighbors. Well, they've already got one neighbor, so you just get a giant circle. So two regular graphs are just cycles. One regular graph is just a bunch of isolated edges. Once you start getting to three regular, you start to see interesting things. What do you think this is going to look like as d goes to infinity? It's going to go to the semicircle. And you can see it over here. This factor over here on the outside becomes essentially d over d squared. And then on the inside, we get 4d minus x squared. And so here is looking at what's going on when d equals 6. And you can see it looks a lot more semicircular. And so as you increase d, very quickly it starts looking like the semicircle.
Is this independent of the size of the graph?
It'll be approaching some limiting formula. And then what really governs the shape of the limiting formula is d, not n. And it sets in fairly quickly. So the last is by 4 authors. One of them is Stephen Miller, but it's not me. It's my colleague, the other Steve Miller, or the original Steve Miller. And this is looking at the spacings between eigenvalues of 3 regular graphs and the GOE. And again, very different spacings between events, but you're seeing the same universality in spacings. I'm sorry, difference in terms of the number of events, different distribution, but very similar in terms of spacings between events. So this is some of the more exciting stuff going on right now in number theory and allied fields. This remarkable universality across problems. All right, so introduction to L functions. So normally, you start off with the Riemann zeta function. I think it's a requirement that you have to start off with the Riemann zeta function. It's a good thing to start with, right? You can get a lot of intuition from this. And then what you want to do is, after you understand the Riemann zeta function, you want to try to figure out which properties really matter and extract from them. So for us, what really matters is we have this product form. We can write the Riemann zeta function as a sum over integers or a product over primes. It has a functional equation. How do we prove the functional equation? We used a lot of Fourier analysis. We used the Poisson summation formula. That's one of the more popular ways of proving this. The Riemann hypothesis says all the non-trivial zeros have real part 1/2. And the observation was that the spacings between zeros appeared the same as the spacings between eigenvalues of complex Hermitian matrices. If you looked really carefully, you should have seen slight changes in the slide as I advanced. This is looking at a more general L function. We just put an an here now rather than a 1. We now have a product over these local factors. We have a functional equation. We have a Riemann hypothesis again. And so this is one of the more famous graphs. This is by Andrew Odlyzko, looking at spacings between adjacent zeros of the Riemann zeta function and spacings between eigenvalues of complex Hermitian matrices. And just an incredible agreement between the two. And so for a while, everybody was using complex Hermitian matrices to model zeros of L functions. And let me give you a quick idea of how we can start attacking these problems in the Riemann zeta function. So complex analysis would be very useful here. Fortunately, we did a small amount of it. So in complex analysis, you always want to integrate logarithmic derivatives. This is beautiful in terms of getting contributions of zeros and poles. And so zeta prime over zeta is basically the derivative of the logarithm. We have two ways to represent the zeta function. The Euler product is the way to go here because logs and products love each other. And now we get the derivative of a sum. So now we take the derivative, we expand with the geometric series. We've seen this many times before. We have a main term, and then we have something else that's easily controlled. And now we integrate term by term. So if you notice, this is very similar to when we were doing the prime number formula. Here I'm integrating against x to the s over s. But instead of integrating x to the s over s, I could integrate over more general function phi. And this is now where we're getting into the current areas of investigation in number theory. So you put in this function phi, and the question is just which functions phi can you actually handle? Well, let's look at what's going on the right-hand side. On the right-hand side over here, we have the integral of phi of s times p to the minus s. Well, I can write p to the minus s. I write p as e to the minus s log p. And then we write s as sigma plus it. And if you notice, we basically have a Fourier transform on the right-hand side with a little bit of a shift. And so what we get is we get integrals of the zeros. We have integrals of the zeta prime over zeta over here. When we do our contour shift, we're going to get the contribution from the residues, which will be phi evaluated at the zeros and the poles. And on the right-hand side, we're going to get phi hat, because we have a Fourier transform, evaluated really related to the primes. And so this is going to give us the analog of the explicit formula. This is the analog of the eigenvalue trace lemma. It allows us to go from understanding the coefficients to understanding the function. Now here, the coefficients are all 1, because all of the stuff in here is just 1 over p to the s. But in general, you would have weights over here coming from the function. Okay, and so we end up getting a formula like this for the Riemann zeta function. For Dirichlet L functions, we get a formula like this. We'll have sums over the characters. So this is the coefficients of the L function. Okay, so cuspal new forms, we get a different expression. Do you guys want to hear a little bit more about correlations and stuff, or do you want me to go straight to Dirichlet? Correlations. So what we can do is, let's say we have an increasing sequence of events. Think of them as eigenvalues, think of them as energy levels, think of them as zeros. One of the ways we can understand them combinatorially is I'd love to talk directly about spacings between events. That's too damn hard. What we can do, which is a lot easier, is to talk about what we'll call the n-level correlations. And so it's how often, if I give you a given tuple, do these differences lie in a box? As you go higher in number theory, you learn that this is a horrible thing to do. Boxes are very tough to work with because they have sharp cutoffs. Either you make it or you don't. Sadly, a lot of things in life have a sharp cutoff. You pass your colloquium, you don't. You get admitted to Williams, you don't. You don't have 95% of you has been admitted your next year. But from a number theorist perspective, that's a lot easier to work with. Where rather than having these sharp cutoffs, we have these very rapidly decaying cutoffs. We've seen this when we did things with Fourier series. We saw this was with, I think, the equidistribution of n alpha mod 1. Is rather than having the sharp cutoff, it's exactly in the interval alpha beta, we looked at alpha beta, and then we went epsilon to each side, and it really dropped off fast, but this gave us a continuous function to work with, and if we wanted, even an infinitely differentiable function to work with. And so what we can do is we can ask, how often is this difference in a box? And it turns out if you can understand this for all the different correlations, the 2-level, 3-level, 4-level, 5-level, you can then use combinatorics and get the spacings between adjacent events. Because right now I'm not assuming alpha j2 is the next event alpha after alpha j1. It's just some event. And so here's a couple of the results. So the first is that the normalized spacings of the zeta function look like the spacings between eigenvalues of GUE matrices. Complex mutation matrices. Montgomery proved that the 2-level correlations of the zeta function agree with complex mutation matrices. Hedgehog proved the 3-level agree. Right at the same time as Hedgehog was doing this, Rudnick and Sarnak proved not only the 3-level, but the n-level agree, and not just for the Riemann zeta function, but for all cuspidal automorphic L functions. So in massive generality, figuring out how to handle these combinatorics. But it was on the order of 20 years from Montgomery's work before we had the Hedgel, Sarnak, Rudnick work. The n-level correlations for the classical compact groups, Katz and Sarnak showed that these are the same for all the classical compact groups. So when you say things look like complex Hermitian matrices, you could also say they look like unitary matrices or orthogonal matrices. As the size of these matrices get large, they all have the same behavior. This is very disappointing. But it turns out that there is a better statistic to look at. This statistic is insensitive to finitely many zeros. So this is one of the main themes of number theory, is to try to find what's the right thing to look at. Well, the problem is if you go very high up, everything is looking the same. What you want to do is you want to look at a place where they're different. And it turns out the place where these functions are the most different is near the central point s equals 1/2. They have very different behavior here. Well, if I'm looking at the correlations like this, let's say I'm just looking at the two-level correlation, so I just care about the difference alpha j1 minus alpha j2 over n. The zeros are getting further and further away from the central point s equals 1/2. If I throw away the first 10 billion zeros, in the limit as n goes to infinity, it's not going to affect the limiting behavior. This statistic is insensitive to the behavior of finitely many zeros. Unfortunately for us, it's those finitely many zeros that are the most important zeros to look at. The action is happening at the central point. That's where the arithmetic lives. So these statistics are not the right statistic to look at. So the right thing to look at is what's called the n-level density. And so the n-level density is taking a Schwartz test function. So this is a function that decays extremely rapidly, and all of its derivatives decay extremely rapidly. And we normalize the zeros so that they have mean spacing 1. If you want, think of phi as a Gaussian. If you're 5 standard deviations away for the Gaussian, for the standard normal, the probability is insignificant. If you're 12 standard deviations, your probability textbooks don't even list the probability anymore. It's that small. And so here, only the zeros that are really close to the central point matter and contribute. And so individual zeros now contribute in the limit. Most of the contribution is from the low zeros, the zeros near the central point. The problem now is each L function only gives you a couple of zeros to look at. So what you have to do is you have to average over a family. And so again, this is another common theme we've seen in the semester. When we were studying primes in arithmetic progression, we couldn't look at just one L function. We had to piece a bunch of L functions together and use that to study primes in arithmetic progression. So what you often want to do is you want to take the object you care about and you want to situate it in something larger. Why do we want to do this? Because we can then use averaging techniques. To try to understand what's going on for one particular thing is damn hard. But if we have a lot of things at the same time that are similarly behaved, there's a hope of some kind of averaging formula kicking in. And that's what is going on over here. And so the Katz-Sarnak conjecture is that for a nice family of L functions, the n-level density depends only on the symmetry group attached to the family. All right, I'm going to try. Let's see if I can try to click over here. No, it doesn't. All right, so I'll try it one last time. Okay, there you go, it worked. All right, so I'm going to just jump to Dirichlet L functions for the last 5 minutes. So we've talked a little bit about some of this, and I just want to see where this all connects. So we have the trivial character, which is the simplest one I can give. If k and m are relatively prime, m is the modulus, it's 1, otherwise it's 0, and then we extend to all of z. So we've seen these before. If m is a prime, it's actually very easy to write down explicitly what's going on. And so what we would have is we choose an integer L between 1 and m minus 2, and what's going on for the character is given just by, now the laser point is not working, a primitive root of unity raised to the Lth power. So this is where we need to use a little bit of algebra. If we look at z mod mz star, if m is a prime, this group is cyclic. And so if it's cyclic, it's generated. I can write every element as a power of the generator. And the generator is going to be an m minus 1 root of unity. And so now all I do for my different characters is they just raise the generator. It has to map it to something of absolute value 1. Because it's a group homomorphism, there's not that many choices. And so it turns out it just raises the generator to the Lth power. All right, so we have a formula for the L function. It has a functional equation. The epsilon is related to the sign of the functional equation. Here's the explicit formula. So it's proved almost identically to the Riemann zeta function, except we actually have some coefficients that are now involved in the calculation. And now what we want to do is we want to evaluate the sum. So the idea is we want to pass the sum over the family through the test function. So all this coming up over here. We want to pass the sum through the test of the sum of all the chi that are not chi naught through the test function to the characters. And this is where it's extremely nice that we're normalizing all of the zeros by the same thing. They all have the same scale. That makes life a lot easier. We can push the sum past the test function. And so now we just have to average the characters. This was, I think, a homework assignment, right? This was one of the crucial things. So we figured out what the sum is over all the characters. It's equal to m minus 1, because remember, m is a prime, so the number of things that are relatively prime is m minus 1. Well, we don't have a sum of all characters. We have the sum of all the characters, not the trivial character. As the name implies, it is trivial to figure out the contribution of the trivial character. It gives you 1. So you just subtract 1 from it. So I'm writing it as a very nice way. There's always this negative 1 term, and then you have this m minus 1 piece. And now we substitute that into here. And now what I'm going to do is, there should be a minus sign in the second line. It should be a minus 2 over m minus 1 over m minus 2. Oh, no, I'm sorry. No, I think I'm doing it right here. I'm sorry. So now we want to understand how big these contributions can be. So we've averaged over the family. There's no more families. There's no more character sums. We now need to evaluate these sums. So phi hat is the Fourier transform of phi. And the assumption we make is that phi hat is 0 if you evaluate it too far away. So a Gaussian decays rapidly. These are functions of finite support. If you evaluate them too large, it's going to be 0. So we assume that if you ever evaluate it at something larger than sigma, it's 0. And the question is, what's the largest sigma we can do? Ideally, we would be able to do up to sigma equals infinity. If we could do that, we could choose phi to be the Dirac delta functional. It turns out the Fourier transform of the Dirac delta spike is the function that's identically 1. If you could take the delta spike, you could figure out exactly what's going on at one point, at the central point. But then you would have to understand the sum of all primes. We can only understand the sum of the primes up to a certain point. To figure out more is going to involve understanding primes in arithmetic progression in terms of studying how primes are distributed, and we'll see that biases between primes can go into 1 mod m and other things mod m is going to make a huge difference. And so let me quickly show you how you would estimate. Well, the log p over log m is going to be of size 1. Phi hat is going to be of size 1. Once p is m to the sigma, the log of m to the sigma is sigma log m. That's going to be evaluating it at sigma, so the primes don't go higher than m to the sigma. And now we have a sum of p to the minus 1/2. Trivially, if you want to evaluate this, say screw this, let's pretend we're summing over all the integers, not over all the primes. You're losing a little bit by doing this, but fine. And then you get n to the minus 1/2. When you sum, it becomes n to the plus 1/2. So you'll get an m to the sigma over 2. You divide by m. So long as sigma is less than 2, it's going to be fine. The other side over here, unfortunately, the m minus 1 over the m minus 2 cancels. And because of that, damn, now we have something that could be large. But the primes have to be congruent to 1 mod m. What's the smallest possible prime congruent to 1 mod m? M plus 1. And so when you use that fact, now we can replace it as k is congruent to 1 mod m, but k has to be at least m plus 1. So when you do that, the second sum turns out to be very small as well. In terms of trying to get better support, better than sigma equals 2, my colleagues and I were able to do this by using more refined properties of primes in arithmetic progression and biases. And so we were able to calculate up to sigma equals infinity if you assume certain reasonable conjectures. If you assume slightly weaker, we can get up to minus 4,4. I'm not going to go into the calculation for the squared term, but the squared term is very similar. You have two different pieces. It turns out we can actually handle the squared term for all support. And so the research, which we're not going to have time for, only we had 5 more minutes, is talking about the main term in these sums we're using over here. It's this m minus 1. It's this lower order term, this m minus 1, that's coming in occasionally, this prime and arithmetic progression that we really need to understand in greater detail. All right. So it has been a lot